When we were talking about the atoms, one of the trouble that people have with the atoms is that they're so tiny and it's so hard to imagine the scale that the size of the atoms are in size compared to an apple is the same scale as an apple is to the size of the earth. And that's a kind of a hard thing to take. And you have to go through all these things all the time. And people find these numbers inconceivable. And I do too. And the only thing you do is you just change your scale. I mean, you're just thinking of small balls, but you don't try to think of exactly how small they are too often, or you get kind of a bit nutty, all right? But in astronomy, you have the same thing in reverse, because the distances to these stars are so enormous. You know that light goes so fast that it only takes a few seconds to go to the moon and back, or it goes around the Earth 7.5 times in a second. And it goes for a year, 2 years, 3 years before it gets to the nearest other star that there is to us. But all our stars are the stars that are nearby in a great galaxy, a big mass of stars, which is called a galaxy, a group. But our galaxy is, what is it, something 100,000 light years, I think 100,000 years. And then there's another patch of stars. It takes 1 million years for the light to get here, going at this enormous rate. And you just go crazy trying to make too real that distance. You have to do everything in proportion. It's easy, you say, with the galaxies are little patches of stars, and they're 10 times as far apart as they are big. So that's an easy picture, nobody gets it. But you just go to a different scale, that's easier. You know, once in a while you try to come back to Earth scale to discuss the galaxies, but it's kind of hard. The number of stars that we see at night is only about 5,000. But the number of stars in our galaxy, the telescopes have shown when you improve the instrument, we look at a galaxy, we look at the stars, all the light that we see, the little tiny influence, spreads from the star over this enormous distance of 3 light years for the nearest star. On, this light from the star is spreading. The wave fronts are getting wider and wider, weaker and weaker, weaker and weaker, out into all of space, and finally the tiny fraction of it comes in 1 square, eighth of an inch, tiny little black hole, and does something to me, so I know it's there. Well, to know a little bit more about it, I'd rather gather a little more of this tiny fraction of this front of light. And so I make a big telescope, which is a kind of funnel. The light that comes over this big area, 200 inches across, is very carefully organized, so it's all concentrated back so it can go through a pupil. Actually, it's better to photograph it, or nowadays to use photocells, they're better instruments. But anyway, the idea of the telescope is to focus the light from a bigger area into a smaller area so that we can see things that are weaker, less light. And in that way, we find there's a very large number of stars in the galaxy. There's so many that if you tried to name them, 1 a second, naming all the stars in our galaxy, I don't mean all the stars in the universe, just this galaxy here, it takes 3,000 years. And yet that's not a very big number. Because if those stars were to drop $1 bill on the Earth during a year, each star dropping $1 bill, they might take care of the deficit which is suggested for the budget of the United States. So you see what kind of numbers we have to deal with. At any rate, I think that the numbers are a problem in astronomy, the sizes and numbers, and the best thing to do is to relax and enjoy the tininess of us and the enormity of the rest of the universe. Of course, if you're feeling depressed by that, you can always look at it the other way and think of how big you are compared to the atoms and the parts of atoms, and then you're an enormous universe to those atoms, so you can sort of stand in the middle and enjoy everything both ways. But the great part of astronomy is the imagination that's been necessary to guess what kinds of structures, what kinds of things can be happening to produce the light and the effects of the light of the stars that we do see. And I could take an example, an historical example. See it many times in science, by using imagination. You've imagined something which could be, according to all the known knowledge of the laws, and you don't know whether it is yet or not. And that's very interesting. There's a creative imagination, you like to call it, not just imagining things that are relatively easy, but something different. And to take an example of a star, as we understand it, an ordinary star like the sun is a great big ball of gas, of hydrogen. It's burning up the hydrogen and so forth, and it's an enormous mass of gas. And it's held together by gravity. You don't have to always understand gravity as curved space. It's good enough for this purpose that force inversely is square of the distance. When things are closer together, the force is stronger. And it pulls everything together. By the way, that's why the world is round, because the globe of Earth is pulled together as much as possible, and if it had a great mountain and an irregularity of a bump or something, it would be pulled in by gravity and it all gets smooth. Rocks aren't strong enough to hold a bump much bigger than a few miles, and Mount Everest is our biggest bump. But on the moon, where the gravity's less, the bumps are higher, the mountains are bigger on the moon.